Have you tried the questions? Not yet. Okay, no issue. I do have few questions. We will see that. Just hold on. Okay. So we were here, somewhere here last class. Right? So we are here somewhere last class. So we have seen few things, right? In theories of failure. We have seen what is a failure, right? Why theory of failures are required. We have seen maximum principal stress theory. Right? Just hold on. Yeah. We have seen maximum shear stress theory, and we have seen maximum distortion energy theory. Right? So apart from this, there are two other theories which are not very important because they are not very much used, right? And hence there is not much questions from this, right? But still, let us know these theories and let us know the small side questions that might be asked from these theories, right? So the fourth theory we will talk about is the maximum principal strain theory. Maximum principal strain theory. It is also known as the Saint-Venance theory. It is also known as Saint-Venance theory. Right? So according to this theory, a ductile material begins to yield when the maximum principal strain reaches the strain at the yielding occurs in simple tension. So all of us know at least what is a simple tension test, right? All of us know what is a simple tension test, right? So it is carried out in the universal testing machine, right? So in the universal testing machine, so whenever the tension test is being carried out, right? The point, the strain at which the yielding occurs, when a ductile material reaches that point, that strain, just hold on. When a ductile material, just hold on, give me 1 minute. Just give me one more minute. Hold on, guys. I'll just share another PPT. Where I have got some new questions. Just hold on, give me 1 minute. Yeah, I think I have got it. Just hold on, give me a few more seconds. Let's see on my screen. Okay, so let us start from few questions. Let us start from few questions. I don't have it here. Just hold on. Just hold on. Just hold on. It is now. Just hold on. I'm just there. Just about to share. Okay. So can you see the screen now, Guna and Prabhakar? Give me a yes. Fantastic. So let us start. Let us start. Let us start. Sorry for the delay. थोड़ा सा टेक में थोड़ा सा कभी-कभार ऐसा प्रॉब्लम हो जाता है, but okay, fine, good. So we have seen it till yesterday's class, till maximum distortion energy theory. We have seen till maximum distortion energy theory. We have learned where to use. There are two other theories, right? Which are very. It is not asked very frequently. Very seldom you can find questions, or in fact, I have not found much questions because the first three theories are the one which are most practical and gives better result, and they easy to apply, so they are being used, right? And we know which one is the best, right? For brittle material, we are going to use the maximum principal stress theory, which is also known as Rankine's theory, right? For all the brittle materials, we know that for ductile material, right, we can use maximum shear stress theory, right? This is the second best theory, second best. Okay, we have seen what are the disadvantages of this theory. It gives an error of around 15%. Then we have the maximum distortion energy theory, which is the best theory for ductile materials. Is the best theory for ductile materials, right? And we have also seen the formulas, right? These formulas are also important to remember. You will not get direct questions, numerical questions. Mostly, 99% of the questions will be theoretical in nature, conceptual in nature, right? The concepts that I'm covering here will cover each and every question. So if you have gone through the question papers, right, the whatever questions has been shared to you, assignments, right, you would have known that each and every question you would have been able to answer with the just last class. But okay, we will do little bit extra, so that at least if any bouncer comes, you should be able to handle, right? So the next is the maximum principal strain theory, right? This is also known as Salient theory, right? So according to this theory, okay, when we are doing the simple tension test, all of us, all of you, please make sure that you have very clear understanding of the tension test that is carried out in the universal testing machine, UTM, right? So how does the curve goes for a ductile material, right? Something like this. So this is particularly for steel. Okay? This stress strain curve is particularly for steel. Not all ductile material will have similar kind of dip, right? So if you see it for aluminium, the stress strain curve for aluminium will be something like this. Okay? You're not going to have the upper yield point, lower yield point, but yes, you'll have the strain hardening region, right? You'll have the strain hardening region. This is the strain hardening region. You'll have the ultimate strength, then necking region, then you'll have the fracture point. All these things points will be there, but it is not a clear distinction. So why is the stress strain curve? This stress strain curve generally used, you'll find in most of the books, right? You will have this stress strain curve. Why is this stress strain curve used? This belongs to the family of steel. So why is this stress strain curve used? Because it gives you a very clear picture of the different points, right? First, you have the proportionality point, then elastic point, then upper yield point, lower yield point, then the strain hardening region, ultimate strength, proportionality limit, then you have elastic limit, then upper yield point, then lower yield point, then you have the strain hardening region, then you have the ultimate strength, and finally you have the necking region. This is the necking region. देखिए ये बहुत इंपॉर्टेंट है, यहाँ से क्वेश्चंस दे कैन बी वेरी गुड क्वेश्चंस. दिस इज द फ्रैक्चर पॉइंट. They will give you a certain region and they will ask you. They will ask you which reason is this, right? So let us just try to understand this. Whatever is being said in this line, definition. A definition is also important because they ask. I'll show you some questions. Okay, I'll show you some questions. Okay, you'll have to answer those questions based on the whatever you have studied. Now, let us see. Let us come back. Let us come back to the definition. Right? According to this theory, a ductile material begins to yield when the maximum principal strain reaches the strain at the yielding in simple tension test. Right? So what is this? This is basically nothing else but a simple tension test. Simple tension test in universal testing machine, UTM. Okay. Now, when has the yielding begun? All of you please see. All of you please concentrate. When did the yielding begin? This is the point. This is the point when yielding began, right? So what is the strain? This is the strain level. Strain when yielding starts. Yielding starts. This is a strain when yielding starts, right? So if this strain will have some value. This strain will have some value. Let me say the strain is EY, epsilon Y, right? So now under complex loading, please try to understand. Please try to understand, my dear friends. Please try to understand. This is a material. This is a machine element. It is under complex loading, right? There are different kinds of forces acting on it, right? There are different kinds of forces acting on it. Compressive force, tension force in all different directions. There is shear force acting on it, whatever it might be. Okay, whatever it might be. Okay, shear force tau xy acting on this component. So this component is under. This component is under complex loading, right? So it will have some strain. It is going to have some strain. So when the strain in the material, which strain it is talking about? It is talking about the principal strain in this material. The principal strain in this material, when it reaches this value, this EY will have some value, na? This epsilon Y will have some value, some percentage. So when the principal strain for this complex loading reaches that value where yielding has started in the simple tension test, right? At that point of time, yielding will start in this member also. Simple tension test में क्या होता है? What is there in simple tension test? What is being done in simple tension test? It is very simple. There is a specimen, standard specimen is there. There is a standard specimen, and what is done on the standard specimen? You apply simple tension load. On a standard specimen, you will apply simple tension load using the universal testing machine, and you get this curve. This is the simple tension test, right? Only tensile load on a standard specimen. But here we are talking about, right? Here we are talking about the complex loading. Here we are talking about complex loading. So when the complex loading, when the principal strain reaches the value of strain, right, at which yielding occurs in a principal, also in a simple tension test, at the same time, okay, yielding will occur. Right? A definition is little bit important. I will tell you how, why. Okay. I don't know if you'll be able to absorb each and everything or not, right? Because no doubt we are going a little bit fast. You should be given much more time, okay? But still, try to absorb whatever is possible, right? So again, it has a formula. The formula is also important. Sigma 1, that is the major principal stress, minus mu sigma 2 plus sigma 3. It's plus sigma 3. Sigma 2 plus sigma 3 smaller than equal to SYT divided by factor of safety. Okay. So this is maximum principal strain theory, right? So we have another theory, that is the maximum strain energy theory. Maximum strain energy theory, right? The last of all the theories. There are more theories even after that, but those are not very important with respect to our syllabus. Okay, there are more theories like octahedral stress theories also there, but these questions are not being asked, so we'll just limit ourselves to this maximum strain energy theory. Right? So let us go through what is the definition. What does this theory say? Right? It says that inelastic action. What do you mean by inelastic action? Means the elasticity is over. If the elasticity is over, what does it mean? Means plasticity is beginning. What do I mean by plasticity is beginning? It means that the plastic deformation has started. Okay? If I'm saying inelastic action, see, if your concepts are clear, these terms should be very easily understood, right? This means plastic deformation. Plastic deformation. So according to this theory, plastic deformation of a material under complex loading begins when the strain energy per unit volume absorbed at the point is equal to energy per unit volume absorbed by the material at elastic point under uniaxial loading. Again the same. Why I have stressed so much in the last slide? Because the same thing will help you understanding this also. So we know this is stress, we know this is strain. So there's a simple tension test carried on a specimen. This is a standard specimen. On this standard specimen will be loaded on the universal testing machine, and forces will be applied. What kind of force will be applied? Tensile force will be applied. And if it is a ductile material, it will undergo necking, right? Then it will have a cup and cone fracture. It will have a cup and cone fracture. This kind of fracture will happen. Okay, at the weakest point. Okay, whichever is the weakest zone. Generally, the weakest zone will be between this to this. So it could be anywhere. This cup and cone fracture can happen anywhere. It can happen here. It can happen here. It can happen here. Wherever whichever cross section is the weakest. That again depends on the material properties, right? So after the cup and cone fracture, so this force by its elongation will be plotted. Okay, on the stress strain curve. I'm not going into much detail. Okay. So if it is a mild steel specimen, it will look like this. It will look like something like this, right? So what is the elastic point? This is the elastic point, right? After the elastic point, plastic deformation will begin. Almost elastic point and yield point, they are almost the same point. There is not much difference. There is not much difference between the elastic point and yield point, right? So you can consider them to be equal unless and until specified in the equation. So this is where the yielding begins, or you can say this is where the inelastic action begins. After this point, if you load it, it becomes inelastic, means plastic deformation starts. So can you tell me what is the strain energy stored per unit volume? Bolo, what is the strain energy stored per unit volume? Which portion of the graph? This portion of the graph. Strain energy per unit volume is the area under the stress strain curve. It is the area under the stress strain curve. So this area that you can see, right? This area you can see is nothing else but, because this is the elastic point, na? Elastic point. This is nothing else but strain energy absorbed up to elastic point, right? So this strain energy will have some value, right? Let me say the value is 10 joule. Okay. Now you have a material which is under complex loading. Now, अरे simple tension होता तो problem ही था. If it was simple tension test, simple tensions, this kind of loading is there on the actual element, machine element. This kind of loading, simple tension on the actual machine element, there was no problem. We have a standard stress strain curve. We can always find out each and everything. The strain energy absorbed under this complex loading is equal to this much. Okay, this material will start to have inelastic. Means permanent deformation will start. Okay, and it is not necessary. See, therefore, what is the difference is this P and this P need not be same, right? I hope you are getting this point. This P and this P need not be same. It will be much lower for this portion, much lower, because it is under complex loading, right? It will be much. It is under complex loading, right? So, is it clear? Is the main concept clear? Taking your time. Are you trying to absorb it? Or what is it? Good. So apart from that, you'll also have to remember this formula. Okay. If you're falling short of time, okay, what you do, you simply remember the first tree. Because first tree is compulsory. 99% of the questions will be from first tree. Okay. But first tree are compulsory. Okay. One more point I'll give you, add here. One more point I will add here. For maximum principal strain theory, right? For maximum principal strength theory, SYS means shear strength in shear, the shear strength in tension. This ratio is equal to 1 divided by 1 plus mu. So if you take the value of mu as let me say 0.3, so SYS divided by SYT, it becomes 0.77. It becomes 0.77. So you can see the value is more. The value is more than the actual, right? It becomes little bit conservative. What is the actual value? Experimental actual value that is obtained from different experiments. There is 0.57. This is the actual, right? So which theory gives the accurate result? 0.577. That is the maximum distortion energy theory, right? Distortion energy or shear strain or von Mises theory. Right? ये important है. Please remember. These are the points that you have to remember. Yes, good Guna. Very nice. Okay. Similarly, if you see for this, so what is the relationship between SYS and SYT? It is 1 divided by H ही होता है. This is what this type of questions is preferred. 2 times 1 plus mu. Okay, 2 times 1 plus mu. So you please remember this one. Along with this one, definitely what you have to remember is the formula. Formula भी आपको remember करना पड़ेगा, right? And then little bit of definition. Okay, definition definitely you have to remember, right? At least understanding. You should understand. You should not by heart the definition line to line. But one more thing that you have to make sure is that along with the maximum shear strain theory, along with this, you also have to remember the name of the scientist. Many a times the theories are asked. Many a times the theories are asked with respect to the scientist. Okay, so it is important. It is important that we also. Okay? Let us do some questions. Then we'll come back to this. Okay, I want the answer from you guys. Let me see how much you remember. So this is question number 1. Tell me the answer for question 1 and 2. Tell me the answer for question number 1. Prabhakar. What about you? Very nice. Good. Right? So question number 2, tell me the answer. We have studied, we have seen this yesterday. We have really tried to understand it in full. Not suitable for ductile material. थोड़ा सा you'll have to think also. ठीक है? If you have paid attention in the class, हो जाएगा. Good. Pravakar is saying D. What about Kunal? Let me try. So I'll tell you the logic. Okay, I'll tell you the logic. Maximum shear C. Ductile materials fails because of shear. Ductile material fails because of shear. So this is definitely going to be the not the answer. What is it being asked? Not suitable. Not suitable for ductile material. Right? Then strain energy. Okay, total strain. So if you see total strain means normal strain plus shear strain. So it has given some amount of it has given some amount of focus to shear, right? So some amount it is given some amount focus to shear. Okay? Shear it has given some amount of focus. Okay? Let me think about this principal strain theory. Okay? If you remember the formula, let us go back to the maximum principal strain theory. Okay, maximum principal strain theory. This is the maximum principal strain theory. It is using sigma 1, sigma 2, sigma 3. Now you would be remembering to find out sigma 1, sigma 2, sigma 3. If you want to find out all three, right? If you want to find out all three, you're using the shear stress to some extent. Formula, just remember the formula, right? Remember the formula. So, ये भी some. It is also not good for brittle material, so not good for ductile. This is okay. If you say about principal strain theory, it gives you satisfactory for brittle. But for ductile, you will generally not use. Will prefer not to use it for ductile. Cannot be applied. But when in this type, I very purposefully taken this question. All the other questions are very easy, direct, straightforward question. I very purposefully taken this question, okay, because I want to explain you something. Okay. Out of all these four, if you see maximum principal stress theory, okay, it is using only one of the principal stresses. Let us go back to this. It is just using the single principal stress. It is just completely ignoring each and everything else. It is completely ignoring each and everything else, right? So if you see among all the options, okay, which is the worst possible option for ductile materials? That is what you have to select. Which is the worst possible option for ductile materials? Are you getting my point? Right? ये तो definitely नहीं हो सकता. This is not the answer because shear stress, ductile material fails in shear, right? So definitely not this answer, right? Total strain, total strain means normal strain plus shear strain. Some consideration is there, right? Now you are left with option B and option D, and both of these are not good for ductile material. But you have to choose only one option. Which option you choose? You have to choose the worst possible, right? So what is the worst possible? That is the maximum principal stress theory, right? What is the worst possible? This is the worst possible. We'll never use it for ductile. Okay, so similar kind of questions will also come sometimes, because PSU questions are they do give you similar kinds of questions, right? Where you might get confused. See, all the other questions you can directly answer, take a one line answer. By if you have attended yesterday's class, you will not face a single problem in other problems, right? So this was little bit tricky. I thought I will explain it to you in class. So I hope it is clear now. Question number 3, we are going to attempt it. Okay, after we have to do little bit of theory. After that, we will attempt it. Question number 3. Okay, all of you try question number 4. Tell me. All of you try question number 4. Tell me. Of which theory is it asking about? It is asking about von Mises. So you see, if you don't know which one is the von Mises theory, you will not be able to answer. If you know which theory is the von Mises theory, do you remember which theory is the von Mises theory? Rushikesh has given the answer as B, but I am a little bit doubtful. Okay. First, let us check which is von Mises theory. Okay. Which is von Mises theory. That is why I have already told you you have to remember the name along with name of the scientist along with the name of the theory. So this is the formula. So you can see direct formula based questions are also being asked. You can rearrange this formula a little bit. थोड़ा सा ये तो rearrange करना है. यहाँ पर in the given question the factor of safety is used as 1. So you can simply say sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square is equal to 2 times SYT whole square. Okay. To be precise, it should be smaller than equal to, this part should be smaller than equal to. Okay. While solving numericals, we'll consider them equal to, otherwise it will mainly be small. So you have to search this one in the option. Right, Guna? Very nice. Okay, this is maximum distortion energy theory. Now you should be able to answer the question. Question number 4. See, everything. See, if your theory is clear, whichever question, if your concepts are clear, if your basics are clear, if I give you 100 questions on these things, you'll be able to solve all the questions. So the most important point is to have very good understanding of the basics. Rusikesh, you have seen the yesterday's lecture. You've gone through the recording. I hope so. Rusikesh Deshpande. Good. Prabhakar had already answered. Okay. Because otherwise you might be finding it a little bit difficult. No worries. Anyways, we are going to start a new chapter today. Okay. It is just about matter of another 15 minutes. Again, we will do this. Okay. ये question repeat हो गया. No issue. Okay. Tell me about this question. This question got repeated. We'll see this question now in short way. Designing of power transmission shafting is based on shafting नहीं होना चाहिए actually shaft होना चाहिए. It is a noun, not a verb. I didn't get you, Prabhakar. So it is 3D object. The Height's theory नहीं होगा actually Higgs theory होगा. They might have misprinted in writing it. Good. Now you get to know what is Saint-Venant's theory. What is Saint-Venant's theory? You have already seen it in today's class. Saint-Venant theory, right? There's a maximum principal strain theory, right? What is Higgs theory? You can say Higgs theory is a maximum strain energy theory, right? What is Rankine's theory? Rankine's theory is, you have seen it in yesterday's class. Rankine's theory is maximum principal stress theory, right? So we now know, all of us now know that these three theories are not suitable for ductile materials. So all these three will be cancelled out. Okay? Saint-Venant's theory, Rankine's theory, Higgs theory, all these three will cancel out. So answer will be A, right? So I'm putting a variation now. थोड़ा सा variation में डाल रहा हूँ. Question number 6. The same question in place of option D, in place of Henke's theory. Suppose I'm writing von Mises theory. So what would be the answer? Answer would be D, right? We have seen it in last class that von Mises theory, that is the distortion energy theory, is the best for ductile materials. This is the best, and this is the second best. This is the second best, right? So definitely we'll go with the option D in this case. But if option D is not this one, it is not given, okay, then we will go with option A, right? We have clearly seen this. Okay? So with this much of knowledge, you will be able to answer. See, formula is being asked, right? Formula is being asked. Many a times you will see that in 1-2 questions, not much, in 1-2 questions, they've asked the definition kind of thing. Okay? The relationship between yield strength and shear strength, that is being asked. Okay? Which is suitable for ductile material, which is suitable for brittle material, this kind of questions have been asked. Okay? So these are very repetitive kind of question, and this is a very short, you can say, chapter where if question is being asked, you can easily score marks. Okay? You can easily score marks. Okay? Now let us come back to the comparison between the theories of failure. Okay? Let us come back to the diagram. Okay? Diagram means we can represent these theories of failure in diagrams. Let us try to have a brief understanding. Let us try to have a brief understanding of the diagram. Okay? So we have x-axis and we have y-axis. ठीक है, you can see. Just एक बार थोड़ा सा diagram को देख लो आप. ठीक है. What do you feel like? ठीक है. What do you feel like this diagram? On x-axis, what we are representing is sigma 1. On y-axis, what we are representing is sigma 2. X-axis, we are representing sigma 1. Y-axis, we are representing sigma 2. Right? Now we have equations for each and every theory, isn't it? We have equations for each and every theory. So when you plot the equations, if you have equations, you can always draw a graph, yes or no? What is the equation of a straight line? Ax plus by is equal to c. This is the equation of a straight line. Similarly, you have equation for ellipse. X square by a plus b square by y square by b is equal to c square. That is equation of an ellipse. Right? Similarly, you have equation for each and every shapes, right? So when you plot, now I will not get into detail how to plot this because it will take so much of time. It will be complete waste of time for this HL exam. I'll not go into those details, but yes, please remember these few things. Okay, na? This is the red one. You can say that is a Rankine theory. What is the Rankine theory? Rankine theory means maximum principal stress theory. Maximum principal stress theory, you can see it is a square. So now let me talk about this square only. Okay, just try to focus on this red square. Just try to focus on this red square. So what does it mean? What this square represents? It represents if your stress value is within the square. If your stress value is within the square, there won't be failure. Stress value means sigma 1, sigma 2. If it is within the square, there will be no failure. If your stress value comes outside the square, that material will fail. Outside the square, what do I mean by outside the square? Your combination of, if you take any point, yeah, if you take any point, let us take any point. What is this point? Let me say this point is A. So it will have two, how to write the coordinate? Sigma 1, comma sigma 2. This is the coordinate, na? Sigma 1, comma sigma 2. What is sigma 1? The major principal stress. What is sigma 2? The minor principal stress. If it comes here, if the combination, if the point sigma 1, comma sigma 2, if it lies outside the square, and you can plot, na? You can plot the graph. You can plot a point. All of us know how to plot a point. X-axis mein and y-axis. Suppose 5, 5. You have to go 1, 2, 3, 4, 5. Then 1, 2, 3, 4, 5. Then you will get a point. That is 5, 5. So similarly, if you plot sigma 1 and sigma 2, and if it lies outside the square, then in that case, it will fail. If it lies inside the square, it is not going to fail. Okay. I hope you are getting it. What does this thing, what does this square means? Okay. What you have to do is remember the shape. That's it. What you have to do is remember this shape. Right? So what is guess theory? Can you tell me what is guess theory? Which one is guess theory? Yes. Maximum shear stress. So what is the maximum shear stress shape like? If you plot the equation that you have received in maximum shear stress, that is guess theory, what you are going to get is a hexagon. What you are going to get is a hexagon. ठीक है, अब देखते हैं थोड़ा सा hexagon. Let us see this hexagon. So this is how the hexagon looks like. The maximum shear stress theory hexagon looks like this. ठीक है, so what does it mean? Again, if your combination stress sigma 1 comma sigma 2, if it falls beyond this hexagon, okay, then it will fail. According to shear stress theory, it will fail. If it lies within the hexagon, if the sigma 1 comma sigma 2, the point sigma 1 comma sigma 2, if it lies within the hexagon, it is not going to. I hope you are getting my point. All you have to do is remember the shape. Okay? All you have to do is remember the shape. Then you have distortion energy theory. Now, can you tell me which one is distortion energy theory? The another very important name for distortion energy theory is von Mises. Okay. Many times you'll get this name von Mises. Okay. So what is distortion? What is the shape of this distortion energy theory? When it is plotted on a graph paper, the equation of distortion energy theory का equation है ना? Which one? This one. This is the equation for distortion energy theory. Von Mises. This is the equation. So when you plot this equation, right, when you plot this mathematical equation, what exactly you are going to have is a ellipse. What you're going to have is an ellipse. What you're going to have is an ellipse. And what about the other two? I can share other two also. Okay, if you want, you can remember. For example, if I talk about maximum principal strain theory, it is a rhombus. But if you don't have time, don't remember this. Okay, if you have time, you can remember this. Again, maximum shear strain theory is again a ellipse. But cover up these two things only when you are done with the first three. The first three are most important. That is maximum principal stress theory, maximum shear stress theory, and maximum distortion energy theory. Right? So for maximum shear strain theory, maximum principal strain theory, it is a rhombus. And maximum shear strain theory, maximum, we talk about fourth one, that is a maximum strain energy theory, it is an ellipse. But prefer to remember, at least remember this three. If you remember this three, 99% of your chances your work will be done. Because we use mostly these theories. Specifically, which theory? Distortion energy theory. The best theory which is used in maximum is a distortion energy theory. Okay? So at least first three theories will be very good with all the formulas, right? The shape of the graph, right? And at least the definitions, okay? And their limitations. We have spoken about limitations yesterday, right? So now I think you can answer this question. Question number 3. Question number 3, tell me what is the answer? B. Right? Question number 3 answer is B. Now see, it becomes so very simple. Right? It has become so very simple for us. So that is very important that if you have the concepts, if you know the concepts properly, so things are very simple. Okay? Clearing these exams are very easy. That is why instead of giving you questions, I can give you 500 questions. But if you don't develop the concept properly, if there is a slight change in the question, you will not be able to answer it. Okay? So that is why we are focusing more on the concepts. So tell me, do you have any doubt here? Tell me if you have any doubt here. Good. So now we will enter onto the next topic, that is I'll just get back. We'll start our next chapter. Just hold on till by the time I download the document. Yeah. Okay. I'll start this screen sharing. Just hold on. Okay, this is chapter 2, not chapter 1. Okay. In chapter 2, that is design against dynamic loading. So all of you ready to start? Very nice, fantastic. So we have just done our theories of failure. We have understood the basic concepts of theories of failure. Now you guys should be able to attempt any question that is being asked in your HL exam, right? I'm pretty confident about it, right? So you revise whatever has been taught properly once, and you will be also pretty confident that you will be able to answer whatever is being asked from theories. Okay, we have also done on numerical, the kind of numerical you have seen that can be asked. Now, we are moving on to a second chapter, that is design against dynamic loads. So first we'll understand what exactly is dynamic load, but before understanding dynamic load, let us understand a little bit of static load. So whenever we design any machine component, okay, whenever we are designing any machine component, right, machine component like anything, any part of a machine, be it gear, be it the connecting rod, be it the connecting shaft, be it the transmission shaft, right, be the axles, or whatever you talk about, which are found inside machines, they have to be separately designed. They have to be separately designed for static load and fluctuating load. They have to be separately designed for static load and fluctuating. So there is two different types of designs you have to do. Designing you have to do. You have to once design for static load, then you have to design for fluctuating. So let us first understand what exactly is design for static load. You've already done that in strength of materials. Whatever you studied in strength of materials is nothing else but mainly design of static load. So basically, static load includes two criteria. There are two criteria when you are designing for static load. What are the criteria? The strength criteria and the deformation criteria. The strength criteria and the deformation criteria. Let us have a simple example. For example, it means that this is a machine element, right? You're loading the machine element this way. Now there are 2 points that you need to check to design it for static load. What I'm talking about is static load. So what is the stress generated? The stress generated is equal to force divided by cross-sectional area, right? First, you have to check that the stress generated, right, that is force divided by area, should be smaller than the maximum normal stress. I'm just taking the example of normal stress. Similarity is also for CL stress. Or you can say Maximum, if I'm talking about the maximum stress, this is equal to permissive. Let me tell it, but let me give you a better name, that is permissive. Okay, or what you can say it this way also. This would be smaller than S Y. Whatever stress has been induced, it should be smaller than SYT. Right? Or if you want, you can also add a factor of safety term. If you're not very confident about the material, what kind of material is supplied by the dealer, manufacturer, right? You might not be very confident, though you're doing lot many tests, incoming test, right? Any manufacturing, when we're doing manufacturing, whatever raw material is received, we carry out a lot of different tests on those materials to ascertain the quality of the material. We carry out many non-destructive tests. We do carry out destructive tests, right? Where do we do destructive tests? We carry out the universal testing machine, UTM. Okay? We carry out a destructive test, and we see that the material that we have received is as per the specification we require. But still, all materials will have some kind of faults. You've seen it in material science also. There will be so many defects which are inevitable. Yes, we'll use some amount of factor of safety also. We have to use some amount of factor of safety so that we are on the safer side. So this is nothing else but design against static load with the strength criteria. The strength of the material should be more than the stress generated during its uses. So we are putting this machine element to some kind of machine. The machine is running. So the stress will be generated because of the various loads on it. The stress that is generated, the maximum stress that is generated, should always be less than the SYT. So what is this SYT? This nothing else but material property. This is material property. This is nothing else, my dear, but this is material property. So the stress generated, the maximum stress generated should be always smaller than the material property. Now, just think about the other thing. So this was what we have studied, is the strength criteria. This is what we have studied. This is the strength criteria. There is one more criteria, that is the deformation criteria. What is the deformation criteria now? What is the deformation criteria? Are bolo bhai. What is the deformation criteria? Who can give me the answer? It is not just the stress. It is not just the stress, my dear. The material might not fail because of yielding. The material might not fail because of yielding. Definitely, if this, what is SYT? SYT is nothing else but the material property, is nothing else but the yield stress. So basically, the maximum stress generated should not go beyond the yield stress. Yes, right. Fantastic. Right. Now, if I talk about the deformation criteria, what is the deformation criteria? What is this deformation criteria? Are bhai, just think about like this. It will also undergo some amount of deformation. Delta L is equal to PL by A. And you have seen this formula, na? Delta L is equal to PL by A. The deformation in this bar because of the load P is equal to PL by A. Very famous formula, right? Now, if this material, if this member machine element we are talking about, which machine element? This machine element we are talking about. If the deformation becomes, I'll tell you in a very layman terms, will not go into very complicated thing. If this deformation, what you are seeing here, if this deformation, if it exceeds a particular limit, what will happen? It might not be yielding yet. Yielding nahi ho raha, it is not yielding yet. It has not failed. But the deformation is large. If delta L is large, what will happen? It might, if it goes beyond, if delta L goes beyond your design limit, it will go and interfere in other parts, right? It's possible that it goes and strikes somewhere, isn't it? It is possible that because of this extra extension, the machine gets jammed, right? So this is also something that needs to be taken care of at the time of design itself. It's not just the material is going to fail, it is also the material should not deform beyond a particular limit. That is why you study deformation also. Study PL by AE. A complete chapter on this is there. Deflection of beams. Right? Because if the beams, they start deflecting more than the given limit, what will happen to the bridges? If the deflection is not under control, what will happen to the bridges? Right? So similarly, the way deflection of beams, similarly, the deformation for machine elements is also important. That is also being studied. These two criteria of something. This is what is known as designing for static load. Okay. Now suppose the loads are more complex loading, then you will use theory of failures. ये तो simple हो गया ना. Whatever you are seeing in the picture, it is uniaxial loading. Only one tension load. Very simple to analyze. Very simple to analyze, right? But if it is a complex loading, there are more than one load in more than one direction. What you have to do, you have to find out sigma 1, sigma 2. That is principal stress, major principal stress, minor principal stress, right? Then you have to use the theories of failure, right? Then you have to design it for static loading. You have to see that everything is within limit. I hope you're getting what is the importance of theories of failure. You should be able to link by now, right? Right? So why you have studied the theories of failure is the first chapter. You should be now. This is a transition from strength of metal to machine design. Okay. So under simple loading, uniaxial loading, this is what you are going to study. Very, very simple to analyze. The sigma max, that is P by A, smaller than the yield strength divided by factor of safety, and you also see the delta L is equal to PL by A, smaller than PL by A. मतलब जो भी होगा, ठीक है? The means deformation should be smaller than the design deformation. Okay, so this is for uniaxial. Now for complex loading, what you will do, you will first find out using your principal stress theories, right? You might use Mohr circle. You'll first find out sigma 1, sigma 2, and tau max. Then you'll go to theories of failure. You'll take the help of theories of failure, and you'll check that whatever your design stresses are. Okay, for ductile materials, you'll use maximum distortion energy theory, and for brittle materials, you'll use maximum principal stress theory, right? And using these theories, what you'll do, you'll design. Okay, so this is basically design for static, right? But my dear friends, there's another kind of loading that is known as dynamic load, for which you have to design it separately. This chapter is all about designing against static. You're already done with design against static load. You're already done with design against static load. Now what you will be doing is designing against dynamic load. So first, let us try to understand what is dynamic load, and then slowly we will try to understand why you have to do separate designing for dynamic load. So are you ready to go? Tell me. Give me an answer. Are you still listening? Very fantastic. Very fantastic. So what is dynamic loading? Let us take a simple example. Let us take a simple example. Let me consider a shaft. Let me consider a shaft, and there are two bearings mounted on this shaft at the two ends. Okay, what are this? The pink colors are bearings. Okay. On this shaft, there is a motor. On this shaft, there is a motor, and the motor is rotating the shaft. What is happening to the shaft? The shaft is rotating. The shaft is rotating. So in place of motor, I'm just showing you a load in place of the motor, okay, so that it becomes easier for you to understand. I'm just showing you a load P, because the weight of the motor will be acting downwards. I'm just showing you a weight force P downward direction, right? And what is happening to the shaft? The shaft is rotating, right? Now let me इसको थोड़ा बड़ा कर देते हैं. Now let me mark 2 points. All of you please understand. Let me mark 2 points. Let me take a point A on the top of the shaft, and let me take a point B on the bottom of the shaft. Now what kind of loading is this? right? So what will be this positive bending, right? So what will be the stress on the top fibers? The stress on the top fibers will be compressive in nature. You learn about sagging, hogging in, right? Top fibers mean point A. It is compressive in nature, right? In bending of beams, you learn all these things: sagging, hogging, positive bending. Yes, very nice, Prabhakar. What about point B? The point B will be in tension. The point B will be in tension, right? Now, after half a revolution, what is half a revolution? Half a revolution means after 180 degree, because the shaft is rotating. The shaft is rotating, so it will make half revolution. Then after some time again full revolution. So it is rotating. So after half revolution, what will be the orientation of the shaft? The shaft will look like this. However, the point B now is on the top and the point A is on the bottom. Yes or no? Arey bolo, yes or no? Now the point B is under compression and point A is under tension, right? After half revolution, that is 180 degree. This is the condition. So if you see again after half revolution, the point A will be on the top. It will be under compression. Point B will be under tension. So what is, if you're taking any point, so what is happening to that point? It is going into tension, then compression, tension, compression, tension, compression, tension, compression, tension, compression, tension, compression, tension, compression, right? So when this kind of loading happens, that is known as dynamic loading. Means what was dynamic means? Dynamic means it is changing with time. So this kind of loading means it is changing with time. The loading, the stress is changing with time. Right? So this kind of loading is known as dynamic loading, and this kind of loading we are going to see what unbalancing नहीं हो रहा है. Unbalancing is again that is a different thing. Okay? We are not talking about unbalancing here. Okay? We are not talking about. We are simply trying to figure out what is dynamic loading. Okay? Unbalancing again is a different thing. Unbalancing again it is a different thing. It will happen. That is grading of shafts and all those things we'll see later on. In vibrations, you are going to see grading of shafts. We are just trying to figure out now what exactly is dynamic loading, right? So are you now able to understand what is dynamic loading? When the stress continuously changes with respect to time, right? That kind of loading is known as dynamic loading or fluctuating loading, right? For those kind of stress, okay, you have to design it separately. Why? Because it has been witnessed that if the type of loading is dynamic, if the stress are fluctuating in nature, the material fails much earlier than the yield strength. In some cases, it has been seen that it fails at 1/3 of the yield strength. Scientists got shocked. They were unable to understand initially. Why is this happening? The yield strength is 200. The material is failing somewhere around 70-80 megapascal. The yield strength of the material is around 200 megapascal. The failure is happening at a load of 70-80 megapascal. Scientists were very much confused. Why is it happening? Then they started experimenting and they found out that it is because of the dynamic loading this kind of failure is happening. So that's why a separate chapter came up, and we're going to see why does this dynamic loading causes early failure. Okay. So the main reason is stress concentration. Okay, so we'll see what exactly is stress concentration. Then you will slowly try to understand what is the fatigue failure. Fatigue failure is a failure that happens because of dynamic loading. That is what we're going to see slowly. Okay. So what is that stress concentration? Okay. Now stress concentration is defined as localization of high stresses due to irregularities. Okay, I'll just mark you the points. High stresses due to irregularities present in the component and abrupt change in cross section. Okay, we'll try to understand what this is. Okay, now let me say this is a member. What you can see on screen is member. There is some amount of load. Because of the load, tension load, let me say tensile stress. So what is the stress developed? We'll say stress developed is equal to force divided by area. We assume it to be constant, but it is not constant. Okay, but we are assuming it to be constant throughout the cross section. So this is nothing else but sigma t for the sides. Okay, so this is how what we assume. Right? But suppose we have a small hole. In the sub or in whatever this missing element is. So if you see in the vicinity of the hole, means near the hole, the stresses are much higher. The stresses are much higher than this stress. So what we have done, this element, E element, this element, what we have done, we have cut it into two parts. And we try to analyze what is the stress. What is the stress at this area? We try to analyze what is the stress at this area. We try to analyze what is the stress at this area. So when we try to analyze what is the stress at this area, we have seen the stresses are much higher than the nominal stress that is given by the SOM equation. Strength of material equation has given us some stress, right? What is force divided by area, right? But when we try to see, so how do you see? We generally use strain gauge. You will put strain gauge and you will try to evaluate the strain, and from the elasticity, from the Young's modulus of the material, we will try to calculate the stress. Okay, this is the practical way of calculating stress. Right? What we will do? We will put strain gauge here, and we will use a Wheatstone bridge. Therefore, separate circuit will be there, right? So we'll calibrate it, and we'll get the amount of strain because of the load. So from the strain, if you know the material, definitely we have selected the material. We'll be knowing the Young's modulus E, right? From stress strain relationship, we'll find out the stress. The experimental. Experiment. So the stress that is found near this hole was much larger than the stress that is given us by the basic strength of material equation. So then we got to know, okay, this is the cause. This is one of the cause. Now we are going to get deep into this. Okay, this is one of the cause. So this high localization, this extra stress, this concentration of high stress is nothing else but it's called as stress concentration. This high stress that we see here, this extra stress that we can see here is nothing else. It is called as stress concentration. Okay, well, let us go back to the definition and try to understand. Stress concentration is defined as localization of high stress. You can see this is a high stress, localization of high stress. You can see the high stress here, right? Localization of high stress due to irregularities. What kind of irregularities we are going to see slowly? Okay, and abrupt changes in the cross section. So what has happened here? There is abrupt change of cross section. Abrupt change of cross section हुआ ना इधर, because of the hole, the cross section has reduced abruptly, suddenly, right? That is why the stresses at this area is much higher than the nominal stress. Okay, so this kind of high localization of stress is nothing but stress concentration. Okay, so there is a factor which is known as stress concentration factor, because that is a definition, but we need some value that needs to be assigned. This is whatever you have learned, this is theoretical. How you are going to use this theory in your numericals to calculate the stress. Okay, there must be some numerical term assigned. So what is the numerical time assigned? It is known as a stress concentration factor, right? So it is given by highest value of actual stress near the discontinuity, that is sigma max, divided by nominal stress obtained by elementary equations. That is the strength of materials equation, nominal stress. So what is sigma naught? Sigma naught is a nominal stress that is given by the elementary force divided by area, right? Or if it is complex loading, you have to find out sigma 1, sigma 2. Okay. And what is sigma max? Sigma max is the maximum, highest value of axial stress near the discontinuity. So how to find out this highest value of axial stress? That is through experiment. The experiment se aaya. Okay. So experiments have been carried out on many different materials, right? With different change in cross section. So what are the different change in cross sections possible? For example, there is a hole. There is a hole. Hole can be keyhole. It could be other holes drilled for some purpose. What else? Fillet joint. Suppose this is the material, sudden change in cross-sectional area. You can see the cross-sectional area has reduced for the material, right? So these are the sudden change of cross-section happening, right? So experiments have been carried out for all different cross-section areas, right? And the value of maximum stress has been predicted, and the value of KT is found out. Okay, and graphs have been plotted. Now we have the graphs. Even if you have the design data book, okay, that in the design data book you have these graphs. So for a particular kind of discontinuity, a particular kind of change in abrupt cross section, you can directly use the value of KT and you can find out the sigma max, right? So suppose, for example, here we have to calculate the sigma max. What we'll do, thoda sa jaldi I'm trying to explain you. We cannot get into much detail. Okay, we'll see the size of the hole, we'll see the size of the shaft. Okay, then we'll calculate the nominal stress by elementary sum equation, force divided by area. And for this combination of hole and shaft, we'll go to the design data book. We'll find out the value of stress concentration factor, and we'll say sigma max is equal to sigma naught into the stress concentration factor. Sigma max is equal to sigma naught multiplied by stress concentration factor. Okay, I hope things are clear. So let us see now what are the main reasons for stress concentration factor. Let us now see what are the main reasons for stress concentration factor. Stress concentration are because of variation in material properties. Okay. Materials will have cavities, internal cracks, air holes, foreign particles. All this results in stress concentration. Right? If there is a foreign particle, there are so many defects are there. Because of these defects, foreign particles, what will happen? The bonding in the vicinity of the foreign particle will not be good. Right? So what will happen? There will be presence of stress concentration. Load application at a point or over a very small area. Suppose this is a column and you're applying a load here. So definitely the stress will be very high at this point. Stress concentration. Abrupt changes in cross section we have seen, right? Abrupt changes in cross section we have seen, right? Discontinuous in the component, there will be discontinuous, right? Lot of discontinuous because of material properties, because of defects in manufacturing. Yes, so you're undergoing, you've gone through manufacturing process, you're learning manufacturing processes, right? There will be so many defects in manufacturing, whether it casting, be it machining, be it extrusion, be it forming, rolling, whatever manufacturing process you do, there will be defects, right? Machining scratches because of machining, we cannot get a very good, uh, unless and until we do very good super finishing process, right? Still some amount of minor scratches will always be there, right? The surface finish will not be very good, right? Because of all these things, okay, stress concentrations are formed, and because of which results in fatigue failure. We are now going to see how exactly fatigue failure happens because of stress concentration. So is it clear what is stress concentration, what is stress concentration factor, why it is required, and what are the main reasons for stress concentration? Good. So how to find out stress concentration factor? We have already seen that is to experiment. Okay, we do experiment on different materials, right? And we form a graph, and using that graph, we can actually find out the stress concentration. Now let us see the effect of stress concentration factor on brittle materials, ductile and brittle materials. Let us try to understand this. Okay, this is very important. Okay, or धीरे धीरे or we will keep on understanding more. Okay, धीरे धीरे we will keep on understanding more. Okay. Now effect of stress concentration on ductile and brittle materials. Again, very important. Okay, these questions are asked from these points. Okay. Now under static load, the type of load is static load. We've already seen what is static load and what is dynamic load. Ductile materials are not very much affected by stress concentration. Why? Because it can undergo plastic deformation. I'll try to explain it to you in a fast way. Okay? Let me say this is a material. It is undergoing some, you have applied some force. Now let me say there are some discontinuities here. Just hold on. Let me say there is some amount of discontinuity here, right? So stress concentration is high in this vicinity. Just hold on. I'll put some water in my throat. A bit of irritation. Just hold on. Give me 1 minute. Okay. So let us get back. So suppose there is a discontinuity here. We apply force. Now it is static loading. Only you're talking about static loading. We'll see how it is different for dynamic loading. Now for static loading, what will happen? Because the ductile material has a capability to undergo plastic deformation. Right? After some time, there is small amount of plastic deformation. So what will happen? Right? This because of the plastic deformation. Plastic deformation means it's a permanent deformation. Nah? Permanent deformation means the molecules will get separated from each other. Right? They will take up new positions. So what will happen? Though there is some amount of stress concentration because of the plastic deformation, right? The stress concentration will get little bit diverse. We can say the stress concentration will take new spaces. Before the failure starts, Okay, before the failure starts, right? What will happen? The stress concentration will get divided and it will start taking new spaces. Because particles are moving, na? Particles are moving and they're going to new place and they're getting settled in a new place. They're not coming back. Right? So the stress concentration gets divided. Whatever defect it was, the defects gets divided and they go and settle at some new position. Now they have to create their effect again from starting at the new position. And by the time they reach a particular value, again because of plastic deformation, again they will get shifted from their position. From that position, they will get divided and they will again move to different positions. Right? Again, because the effect of stress concentration gets nullified, again we have to start from zero. That is why under static loading, ductile materials are not very much affected by stress concentration. Is it clear? Is it clear to all of you? Very nice, fantastic. So remember the first point, okay, this is to be remembered under static loading, ductile materials are not affected by stress concentration. And you also now know the reason. Okay. The second is under fluctuating load. Under fluctuating load, endurance limit of the components of made by ductile material are greatly reduced. We'll see what is endurance limit. Endurance limit is a strength criteria for dynamic loading. Right? For example, in static loading, what was the strength criteria? That is the yield strength. So endurance limit is equivalent to yield strength in dynamic loading. We are going to see that. Okay, what is endurance limit? We are going to see. Okay. So now the endurance limit of ductile materials are reduced considerably if there is stress concentration. Okay. Under fluctuating load, the endurance limit of the components made of ductile materials are reduced drastically. Right. And again, the third point, now you should be able to understand stress concentration in brittle material is more severe for both static and dynamic load because of what? Because of their inability to have plastic deformation. We have seen it in last class, right? The brittle materials does not undergo any plastic deformation. That is why the stress concentration, it cannot get distributed, right? It cannot be dispersed, right? So that is why, be it static loading or be it dynamic loading, brittle materials are very prone to failure because of stress concentration. Brittle materials are very prone to failure because of stress concentration. So good conceptual questions can be asked from these points. Under static load, ductile material stress concentration does not have much effect. Why? Because ductile materials can undergo plastic deformation. Under fluctuating load, yes, stress concentration will affect ductile materials. For brittle materials, be it static, be it dynamic loading, stress concentration has the maximum amount of effect. Okay. So these questions can be asked from these points. Effect of stress concentration on ductile and brittle material. Is it clear? Give me a thumbs up. Very nice, fantastic. Now let us go a little bit of calculation part with theory to work further. Let us go a little bit of calculation. Let us try to understand, because numericals might be asked, simple numericals. Okay, it will not be very hard numericals. Simple numerical might be asked. We'll do equations from previous year gate equations. So let us try to understand few terms before attempting numericals. So what are type of dynamic stress? So this chapter is about dynamic stress, right? This chapter is about dynamic stress. So let us try to first understand what are the different types of dynamic stress possible. The first one is called fluctuating stress or alternating stress. The first one is called fluctuating stress or alternating stress. So you can see here This is the zero line. This is the zero line, and this is the zero line, means this is zero, and towards the right it is time, and this is the stress amplitude, or you can say maximum value of stress. This is stress, the value of stress. So how is the stress varying? This is how is the stress varying, you can see, right? So the minimum value is greater than 0 here. Sigma minimum is greater than 0. So if sigma minimum, I'm giving you one criteria. Okay? If the sigma minimum is greater than 0, means the whole stress curve is above the 0 line, timeline, right? Then it is called as alternating or fluctuating stress. The next is the repeated stress. Next is the repeated stress. What is repeated stress? You can see the 0 line where the timeline, that is the x-axis. X-axis is representing 0 stress. X-axis is representing 0 stress. So you can see here the minimum stress is 0. The minimum stress is 0. You can see minimum stress. What is the minimum stress? It is 0. So when the minimum stress is 0, sigma minimum equal to 0, it is called as repeated stress. It is called as repeated stress. The third one you can see. The peak in the top and the least amount of stress in the bottom, they are equal. Just the thing is that this is tensile in nature, this is compressive in nature. Tensile in nature, this is compressive in nature. What is happening here? This is also tensile, this is also tensile. This is also tensile, this is also tensile. Or it can be compressive. Whatever it is, both has to be of the same nature. Compressive, compressive, compressive. Higher means something like this. There's something like this. Let me show it to you. Plus 10 megapascal to 20 megapascal. Then again plus 10 megapascal, then 20 megapascal, 10, 20, 10, 20. This is alternating or fluctuating. 10 to 20. It is varying from 10 to 20. Minimum value is 10, maximum value is 20. So it is going from 10 to 20. Okay. So what is repeated? Repeated is something like this: 0 to 20, then back to 0, then 20, back to 0 megapascal, then 20 megapascal. So this is repeated. This is repeated. And what is reversed? Minus 10 megapascal to 10 megapascal. Then again minus 10 to 10, minus 10 to 10, minus 10 to 10. Then it is called as reverse stress. problem करेंगे तो थोड़ा बहुत you will get to understand. Yes, the soft example was reverse stress. You can see the soft example was reverse stress. Very nice, good. Right. So these are the three types of stresses possible. These are the three types of dynamic stress possible. Okay. So let us see few things. Okay. Let us try to see few things. Few terms which are important. Let us first concentrate on fluctuating or alternating stress. Fluctuating or alternating stress. Let me assign some value so that it becomes easier for you to understand. So this is sigma max. Sigma max is equal to, let me say, 20 megapascal. And this is sigma mean, 10 megapascal. So there are two terms that needs to be defined. One is the stress amplitude, that will be defined by sigma A, and also mean stress, that will be represented by sigma m. What is the amplitude now? All of you please try to see. This is the amplitude. This is the amplitude. This is the amplitude, isn't it? थोड़ा सा graph आना चाहिए हल्का सा. This is nothing else but the amplitude. So how can I write the amplitude? I can write the amplitude as sigma max minus sigma mean divided by 2. I have written the formula. Stress amplitude sigma max minus sigma mean divided by 2. Very nice. Then we have something called mean stress. How to write the mean stress? The mean stress will be sigma max plus sigma mean divided by 2. So this is the value of mean stress. Right, already shown here. This is the value of mean stress. This is the value of mean stress. Sigma max plus sigma mean divided by 2. Average, exactly. Right, average. Very nice. So similarly, let us see what is repeated stress. What is repeated stress? Let us see repeated stress. What is repeated stress? So this is the value of sigma. This is the value of sigma A, that is amplitude. You can see here sigma amplitude. Formula remains same. There is no difference in the formula. Sigma A is equal to sigma max minus sigma mean divided by 2. And what is the value of mean stress? This is the mean stress. Sigma mean stress is equal to sigma max plus sigma mean by 2. And we know that for repeated stress, the sigma mean value is equal to 0. So this is nothing else but equal to sigma max by 2. So this is nothing else but sigma max by 2. Sigma mean, yes, right? Sigma mean 0 इसमें नहीं होगा. Sigma mean will be 0. So this is also 0, you can see. This is also sigma max by 2. So in this case, for repeated stress, the value of sigma A and sigma M are equal. Right? This analysis you can also do it, no issue. Okay. What is the value of sigma M for repeated stress? Tell me. What is the sigma M? What is the value of sigma M for repeated stress? Yes. Don't look at the diagram and tell. ढंग से. Try, focus more. Write down the formula. Sigma max plus sigma mean divided by 2. So in this case, if sigma max is plus 10, what will be the value of sigma mean? Minus 10. Yes or no? I'm talking about the mean stress, average. So what will be the answer? Sigma max and sigma mean will cancel out, so answer is 0. right? So these three stresses, you should have a little bit of idea. Okay? You should have a little bit of idea about these three stresses, three kind of stresses. Thoda sa. We'll talk about questions that are being asked. The questions that can be asked will be numerical in nature, or you might be given this graph. That is also least not very probable, but you might be given a graph and it might be asked the values of this. Okay. And there is one more formula, that is the stress ratio. One more formula, that is stress ratio. So what is the stress ratio? Stress ratio is equal to sigma mean divided by sigma max. This ratio, I remember, it was there in my exam actually, GATE, when I had appeared for GATE writing in 2015 or something like that, right? This was first time being asked, okay? And I didn't know what is stress ratio. Was very confident with this mean stress and stress amplitude, but stress ratio, it was not found in most of the books, right? And never it was asked in GATE before that, stress ratio, right? So I made some guess. Okay, I thought कि ratio है, तो obviously it has to sigma max or sigma mean कहीं कुछ होगा, ठीक है? And options were also as such. 2 था, 0.5 था, तो I thought कि this is what it's going to be, ठीक है? But unfortunately, I didn't know the ratio, and I had done a sigma max by sigma mean, and it was a 2 marks question. I have calculated everything properly, okay? And this is a question I think, no, not GATE. In GATE 2019, it was again asked. Okay, the similar question has been asked, and this time they have given it. It's so good of them. Okay, they have said it R ratio, and they have given it minimum to maximum stress. So it becomes very easy now, right? But I think it was in asked in 2014 or 15. I don't remember the year exactly, right? But at that time they have not given the definition, and it was a 2 marks question. Just everything was calculated just because I have done it maximum by minimum. My answer was wrong. So all of you try this. This time it is 1 mark question. I think that time it was 2 mark question. I don't remember right now. That was the case. It's so sad. Everything was calculated. Only the last point I didn't know, and I made some guess, and that also it went wrong. Saying 0.5, let us see. Okay, let us try to see. Okay. A metric specimen is subject to a cyclic loading. The mean stress, sigma m, is given as 140 megapascal, and minimum is given as 70. Right? So you have to find out minimum to maximum. So minimum is already, you know what is the minimum. Okay? You have to find out the maximum. You have to find out the maximum, right? So we know mean is equal to sigma max plus sigma minimum divided by 2, right? So is equal to 140, right? This implies sigma max is equal to 140 into 2 minus sigma minimum, that is equal to 280 minus of 70, that is equal to 350 megapascal. Right? You have got the value as 350. So how it is 35? No, not 0.5 also. Yeah, you should read the equation properly. ठीक है ना? थोड़ा सा here in just trying to be fast, ठीक है? Might cost you the selection. ठीक है? Speed, along with speed, what is required is accuracy. First is the accuracy, then the speed. right? So what is the R ratio now? Minimum to maximum. So minimum is 70 divided by maximum is 350. So it is equal to minus 1 by 5. Round off it to one decimal place, then it will become minus 0.2. Right? So I hope the things are clear. Okay, I hope the things are clear. So we can continue, but I feel we'll continue next class because it's almost time. I don't know, you might have some other appointments. So these are all we have to study next class. Okay, ठीक ठाक है. It's not like shall we do a little bit more or what? One class, at least one class, you have to be fast. Next class, you have to be fast. We cannot cover up at this speed. You will not be able to cover up everything at this speed because we have 5 lectures. Okay? This is more conceptual. You might be studying this for the first time. That's why I have taken some time. And next class onwards, we have to be a bit fast. Okay? We have to be a bit fast. So, is it clear till now? So, are we able to follow up? Are we able to follow? We are finding my speed okay, but we have to be a little bit fast. There is no other option. Okay? We don't have the liberty of uh, 30 hours class that generally we'll have for machine design. Okay? So we have to speed it up. Okay? Next class will be fast. Okay? I hope so. Okay? So you please revise whatever you studied till now. Okay? You please revise whatever you studied till now. And we have a lot to cover. We have to cover up bearings, clutches, brakes, springs, gears, and joints. Right? These are the chapters that has to be covered after this. And approximately this is our second lecture, so we have 3 another lectures after this. So ठीक है, no issue. We'll be able to do it. Okay then, best wishes. Take care. And if you have any concern, you can put up some review. ठीक है, आप review में डाल दीजिए कोई भी concern है. Feedback, definitely always give the feedback because your feedback reaches us indirectly. ठीक है, and that helps us in fine tuning the class. What happens in face-to-face contact, right? If you have face-to-face contact, we can scan your faces and understand if you're understanding if my speed is slow or if my speed is fast or whatever problems you have, right? But that is not feasible when you are having online classes. Online classes, on the other hand, have many other pros. You can sit at the comfort of your home at this point of time and you can learn things, right? So that is very good advantage. So to minimize the disadvantage, right? Please keep on providing feedback to all your subjects so that in whatever way possible we can improve ourselves to help you better the lectures. Okay, thank you all of you. Okay, thank you all of you. Good night. We shall meet again very soon. Thank you. Good night. Thank you.